All right, welcome to the webinar, everybody. And we're going to be talking about how solar module trends are disrupting off-grid system designs. This is a joint webinar presented by SunWize Power and Battery and Morningstar Corporation. In case you did not see the previous slide when you're waiting, we want to remind you that if you do have a question during the presentation, you can just go ahead and type that into the questions chat box at the bottom of your GoToWebinar pane. I will address those questions at the end. We've also attached a copy of the slide deck that we're using today, and that's in the handout section of your GoToWebinar pane. So if you have not downloaded that now, you can go ahead and do so. And then lastly, we're going to be recording this broadcast, and we'll email you a link to the recording before the end of the day tomorrow. All right, let's go ahead and take a look at the presenters for today. So if we go to the next slide, we see that presenting on behalf of SunWize today is Aerel Rankin, VP of Sales and Technology, and my name is Mark McHenry. I'm a marketing manager presenting on behalf of Morningstar. Let's go ahead and take a look at the agenda for today. After we provide a brief overview about Morningstar and SunWize, we're going to talk about module categories and advantages of module growth, as well as some potential growing pains and the history of solar cell growth. Then we'll share how module growth affects charge controllers. Next, we'll share some real-life examples and talk about temperature considerations, and we'll end with conclusions and the Q&A session. So I'm going to talk a little bit now about Morningstar. And here's just a quick overview. Since 1993, over 4 million of our controllers and inverters have been sold around the world in mission-critical commercial, industrial, residential, and mobile off-grid solar applications. We're considered to be the charging experts with the widest and most diversified product line, and we have the lowest hardware failure rate in the industry. We rely on distributors such as SunWize to help deliver and provide technical support for our products and help design complete off-grid systems and packages that combine our products with modules, batteries, and other components. So I'm going to let Aerel Rankin share a little bit about SunWize and start the presentation about how trends towards larger modules are affecting off-grid solar designs.
Thank you very much for the introduction, Mark. Again, my name's Aerel Rankin, VP of Sales and Technology at SunWize Power and Battery. A little bit about SunWize. We have been around as a brand for going on nearly 40 years. Our primary focus is the design, build, manufacturing, assembly of standalone industrial power solutions. That includes electronic and assemblies for integration into OEM products, as well as a variety of field applications that cover standalone solar battery systems, hybrid solar energy systems that incorporate generators, fuel cells, tags, and other baseload power sources, as well as backup power systems, UPS, and other things for critical load outage applications. We have manufacturing on both coasts and specialize in both custom design power systems to meet our clients' exact specifications and requirements, as well as some pre-designed control panels and solar systems for rapid fulfillment and common applications. On the right-hand side, you'll kind of see a graphic showing some of the common building blocks that we utilize, including outdoor rated enclosures, pre-wired control panels featuring solar charge controllers, as well as mounts and other things like that. So what we're here to talk about today is the implications of growth in the large format module sector. But before we get to that, of course, we want to talk about what do we mean by large format. First, let's talk about the other type of solar module, and that is small format solar modules. These have typically been the mainstay for industrial off-grid applications. They're what we consider nominal for nominal 12-volt charging applications, and they're often in the 5-watt to 200-watt power range. If we contrast that against large format modules, these are typically for nominal 24-volt battery bank charging. They come in 300-watt or greater power classifications, and they've traditionally been nominal 72 cell. If we go over some of the benefits for the small format modules, first and foremost, when you have low power applications that do not require a significant footprint or amount of power, they're clearly the best choice, lowest overall cost. They're also easy to handle and mount due to the low weight and space constraints. They also carry a variety of certifications that are very rare for large format modules, namely Class 1 Division 2 for hazardous location applications. And they also sometimes provide wiring and cable flexibility. If you want to put any specialized cable types, either in or outside of conduit, sometimes having a robust junction box can be helpful. On the flip side, they're typically actually handmade via low volume production. That results in a much higher cost per watt than you get from the economy of scale for large format modules. And sometimes that wiring and cable convenience can actually result in a slower installation compared to typical MC4 quick connects. For the large format, first and foremost, the economy of scale has resulted in very low cost per watt, which of course is something that we're going to take advantage of in the off-grid space in order to support our higher load applications. They've also historically been pretty standardized around both form factor and electrical parameters, which is something of course that we'll be talking about. And they usually come with a more robust suite of certifications, not C1D2, but things like IEC, UL, so on and so forth. And the MC4 connectors typically come standard. Disadvantages are space requirements. And they also have a higher minimum power, which you may in some cases not need or want, or where the downsides outweigh the upside in additional power. And then of course you have shipping cost and risk. These things are not fun to ship, especially in low quantities. So one small format use case example that we want to cover here really quick is for a Southern California utility company. It's for a monitoring application. This is actually an ongoing project. You can see here the array size was about 130 watts using two different 65 watt modules. So for a nominal 12 volt battery application, utilized a SunSaver 20 amp PWM charge controller. In this case, the utility was looking to primarily minimize any sort of risk for wildfire by tapping the 12,000 volts that are available on the utility line. And there were some other considerations as well about off-the-shelf availability and lead time that also factored into their decision. But this is a great example of why and where small format modules continue to be king for these smaller load industrial applications. Just looking at the mount fitment and everything else, it really wouldn't work very well with a large format module for a variety of reasons. Going over to how we typically utilize large format modules, this is an example of one of our off-the-shelf Power Ready Express systems. And this is something that will factor into parts of the later presentation, namely the fact that this is kind of the upper limit of what you can fit in terms of an array size on a side of pole mounting configuration, side of pole being the most common. And so there's a very kind of specific use case and upper limit for this 3 large format modules on a side of pole that again will factor into some of this module growth. This particular design utilizes standard 8D batteries as well as a ProStar MPPT charge controller. And one of the kind of things to note about this system, we SunWize are transitioning many of our pre-existing designs over to MPPT charge controllers that have, in some cases, higher voltage limits or higher power limits in order to give ourselves some headroom growth into these larger modules. You'll also notice that things have been so consistent for so long that we've named these mounts around how many modules they will hold. But now with the growth of everything, you'll note that our 3 module mount can actually hold 2 550 watt modules, which would give you the same overall array capacity here. We'll talk about some of the implications of those design changes as they come up. And then here's just a design map that you can see on the presentation afterwards that shows the sizing limitations for what size loads a system like this would power in different sun zones. So some of the advantages of module growth are that it supports larger loads. So naturally, as the size of the equipment that we're powering goes up, these large format modules have been a boon because they've been continuing to grow in size alongside some of these loads. They, of course, support areas with lower solar resources. They can contribute to better reliability for the system, including what we call the solar safety factor or the array to load ratio. Having a higher solar safety factor will result in a higher average battery state of charge, which will result in longer battery replacement intervals, improving your OPEX costs. Eventually, there will likely be other sources of lowering total cost of ownership, including improvements in the balance of systems, as well as controller sizing optimization. Some of the growing pains may be physical fit and wind ratings for the mounting structures that these solar modules are going on to. Installer weight and handling considerations, whether that may be the way or the application that things are being installed and how a larger module may be limited, or it may have to do with the installer personnel and their ability to lift some of these heavier solar modules. It may even factor into things like OSHA rules around specific weight requirements and how many personnel are required on site. Of course, one of the big ones that we'll be touching on is current and voltage ratings for the charge controllers and how the growing modules can really make a lot of changes there. And that's not just at the charge controller level or the mount level, it can also carry downstream to your circuit protection, fuses, wire sizing, things like that. And then after a long period of time of having fairly predictable and linear electrical characteristics between these different large format modules, we're now seeing a lot more variety and unpredictability in terms of what you're going to get. Okay, so we're going to talk a little bit about the cell history growth. This is really at the heart of what's going on. We've been on a steady march, starting with 156 millimeter wafer sizes, and it's been growing rapidly. What is driving this is primarily design considerations for residential, commercial, and utility scale solar applications. These are the primary market for the economy of scale module manufacturers. They are looking to optimize racking, cabling, installation, foundation, combiner box, and module costs at scale. And if you look at the graphic on the left-hand side, where you'll see these marginal improvements on cost basis for these projects, these differences are achieved by moving from a 540 watt module to a 550 watt module. It is not about the overall power rating of the module. It's about the specific electrical profile of the module and the optimizations that can be achieved at scale, resulting in these cost savings. So to these module manufacturers, we as the off-grid market focused primarily on battery charging and continuous loads, I think it would be generous to consider us an afterthought. We're not what is driving this. We are simply reacting to it. So of course that is illustrated by the volume differential between what we do and everything else. So I just want to emphasize this is what's going on in the background for the manufacturers. It's nothing personal, it's just we're basically being caught up in these changes as they continue to optimize. So within this overall growth that we'll be talking about, there is certainly not a clear picture on the exact timing, but it seems to be that the writing on the wall is fairly consistent, that at least the major players are moving rapidly to these new 210 millimeter designs. In some cases, as much as 80% or more of the modules that are being manufactured at this moment in time are going to be using these full 210 millimeter by 210 millimeter wafer sizes. So these are just a few sound bites showing the kind of prevailing attitude out there about these rapid rises as these manufacturers shift over their manufacturing. This is a chart that really illustrates sort of the rapid change that has come recently. If you look at the x-axis, the growth from 2009 to 2019 was steady and linear, and that was a 10-year period. If you contrast that to the period from 2019 to 2021, significantly shorter period, significantly more aggressive growth. If you were to make that x-axis linear so that it's not spaced out, it would almost be close to a vertical line up since 2019 as we've been looking at some of these larger module sizes. You'll notice at the very top, you've got some of the cell dimensional characteristics moving from traditional half cut 144 up to 158, 166, 180 by 210, and then eventually 210 by 210. So just to illustrate this, starting with what's considered the M0 wafer design size in the early 2010s. This was the traditional 200 watt to 300 watt 72 cell module we were all familiar with. That ultimately gave way to the M6 wafer design, which was supporting these 300 watt to 380 watt modules, which I think a lot of us are still playing primarily in this power range. And then recently we started to see the M10 wafer design, and now you'll see a lot of module availability in the 400 watt to 450 watt range and starting to push up beyond that. And now we're seeing introduction and manufacturers focus on this new M12 210 millimeter wafer design, which is essentially modules in this 560 watt to 680 watt power classification. You'll notice the dimensional changes have grown significantly along with weight. And so now that we've kind of set the background a little bit, we're going to go into some of the charge controller considerations, and I'm going to turn it back over to Mark to speak a little bit about the Morningstar side of things on this.
Okay, thank you very much, Aerel. So we're going to take a look at how module trends over the years affect charge controller choices. Modifying your system designs to include newer modules can affect your charge controller decisions depending on how much higher the short circuit current ISC ratings and open circuit voltage VOC ratings of the newer modules are. And the effect also depends on whether the controller uses PWM or MPPT charging technology, and it also depends on the manufacturer or controller brand. So if we just take a quick look at this slide here, this next slide, I just wanted to point out, if you fail to account for changes in PV array current and voltage inputs when swapping in new modules in old off-grid system designs, there may be consequences. Both of these mistakes that you see here, the exceeding charge controller current ratings and exceeding charge controller VOC ratings, both of these mistakes have consequences, but exceeding charge controller VOC ratings is more problematic, much more problematic, as we'll see on the next several slides. So first we'll cover the failure to address the changes in PV array input current and the effect it has on PWM controllers. Increases in module sizes can lead to increased PV input current beyond the charge controller's charge current rating, which causes many PWM controllers to shut off charging. This is not to say that the controller is powering off, it's shutting off charging. And this slide illustrates an example where every few years an off-grid system design swaps out an existing module for a newer, larger module. The incremental changes from year to year don't cause any problems until finally the module's input current reaches a limit that's too high for the charge controller to handle. And the controller shuts off until the input current reduces to acceptable levels. And let's take a look at a few different scenarios that describe PV array input current versus charge controller current rating and the results. So you can see this next slide is up. And in the first scenario that you see here, the PV array current input is often greater than the controller charge current rating. This is not recommended because over time, this does not have a good effect on the charge controller. It's not healthy for the charge controller in the long term. And aside from that, most charge controller brands will shut off as soon as PV current input is greater than the controller's current rating. When the controller is off, and what I mean by off means that it's shut off charging, none of the power from the array during this high power time is delivered to the batteries. And then in the second scenario, the PV current input is only occasionally greater than the controller current rating because of perhaps a short-term rare occurrence. And an example of a rare occurrence, or an occasional occurrence, I should say, could be caused by an edge of cloud effect. And we'll describe what that looks like on the next slide. So if we go to the next slide and look at the edge of cloud effect, this can cause an increase in PV current input. So what's happening is when a cloud appears at just the right position in the sky, refraction of sunlight through water droplets in the cloud is directed to the solar array at a 90-degree angle of incidence, the most intense angle. And this refracted sunlight plus the other sunlight coming on a direct path from the sun causes the array to deliver more current than the array's calculated high current under normal conditions. So for this and other reasons, many controller manufacturers recommend multiplying the normal high array current input by a factor of 1.25 to determine the recommended charge controller current rating to adequately support current input from the array. Now, fortunately, Morningstar's ProStar PWM and TriStar PWM controllers have overcurrent protection, continuous duty rating, and current limiting features that already account for these occasional edge of cloud effects. The ProStar and TriStar will continue to operate at up to 130% of their charge current ratings without shutting off. So taking a look at the next slide and continuing where we left off, you can see that the Morningstar controllers in row 2 of this table, you can see how they continue to stay or continue to charge and harvest this very high energy. And then in the last row, you can see that if everything else is right with your system, all controller brands should stay on and function properly if the PV current input is always less than the controller current rating. Now, the only exception, or one exception, would be if the controller started to deteriorate over time. But as far as the ProStar and TriStar controllers are concerned, they have a 5-year warranty, and many of them have been in operation for 10 to 15 years or more. So you're good there. All right, now similar to our PV current input example, increases in module sizes can lead to increased PV input voltage beyond the charge controller's VOC limit, which can permanently damage the charge controller and render it useless. So this slide illustrates an example where every few years, an off-grid system design swaps out an existing module for a newer, larger module with a slightly higher VOC rating. The incremental changes every few years don't cause any problems until finally the module's VOC reaches the limit that's too high for the charge controller to handle, and the controller is destroyed. And it seems like somebody was off mute there for a second, so we had a little disturbance, but it seems like it's quieting down now. Okay, great. All right, so let's move on to the next slide, and you can see, I guess the point I want to make here is that you can use a string sizing calculator tool, and that's in the link near the top of the slide here in that red section. And you can use that string sizing tool to help you make sure that you don't exceed a charge controller's VOC limits on the coldest days of the year when array VOC is the highest. Morningstar MPPT controllers VOC limits are pretty straightforward. They aren't dependent on the battery voltage in your system. Morningstar PWM controller VOC limits, however, those do depend on the size of the battery in your system. And on the next slide, we're going to look at the VOC limits for our TriStar PWM and ProStar PWM for different battery voltages. For 12-volt battery systems, the max VOC for the TriStar PWM and ProStar PWM controllers is 30 volts. For 24-volt systems, the max VOC for both of these PWM controllers is 60 volts. And then for 48-volt battery systems, the max VOC for the TriStar PWM is 125 volts, and the ProStar PWM does not support 48-volt batteries, so that's not applicable. And I included these slides in the deck to help make sure that you know and don't exceed your max VOC limits for these PWM controllers, depending on whether the system uses a 12, 24, or 48-volt battery system. All right, so with this information, let's go ahead and take a look at a very simple example. In this example, we're supposing that you have an old 24-volt battery off-grid system with 2 modules connected in series, and the VOC rating for a single one of these old modules on the coldest day is 29 volts. From the previous slide, we remember that the TriStar MPPT controller's VOC limit is always 150 volts regardless of the battery system. The TriStar PWM and ProStar PWM VOC limits do depend on the battery system size, and for 24-volt battery systems, their VOC limits are both equal to 60 volts. And since the old array maximum VOC is 29 volts times 2 modules in series, which equals 58 volts, all of these charge controllers meet VOC requirements for the system. However, if we replace the modules with new modules that each have a VOC rating of 40 volts, the new array max VOC is 40 volts times 2 modules in series, which equals 80 volts. And you can see that the TriStar MPPT is the only controller that meets the VOC requirements of the new array. So with that said, let's address another topic that relates to larger module trends in charge controllers, and that topic is oversized PV arrays. And specifically, what we're talking about using MPPT controllers with arrays that have power outputs that are higher than the charge controller's nominal maximum operating power. Now, the good news is that PV input power can exceed the controller's maximum operating power without damaging the unit. We generally recommend 30% or less as the cutoff for how much you should oversize your arrays. The controller will limit output current at its output current rating. Array oversizing enables more power for battery charging on sunny days and on cloudy days. And let's take a look at an example. So in this example, one 350-watt module is connected to a ProStar MPPT controller with a maximum operating power of 350 watts. If the existing module is replaced with a new 450-watt module, the question is, can the ProStar MPPT charge controller still be used in the system? And the answer is yes, because you can oversize your arrays when using Morningstar MPPT controllers. And on the next slide, we're going to take a look at a graphical view of what's going on in this example. So here we're going to share an example of the extra power that's generated by an oversized array on a perfectly sunny day at standard test conditions. We're comparing a 350-watt module represented by a black curved line to that of a 450-watt module that's represented by a blue line. And when using the 450-watt module, even though the power being delivered to the battery is limited to 350 watts, and the red area that you're starting to see here now at the top of the production curve, this represents lost power. The larger 450-watt module is still harvesting more energy than the 350-watt module as shown in the green area that you're now seeing displayed. So the larger module will provide more power early and late in the day, and the same power in the middle of the day as compared to a smaller module. All the power gained by the larger module as represented in the green area is available to charge your batteries. Now again, this is an example that assumes a perfectly sunny day, but what happens on days when it isn't clear and sunny? So we'll go to the next slide to take a look at this. So this graph depicts what happens on days with intermittent sun and clouds for the 350-watt and 400-watt modules. On these days, there's going to be little or no power shaving, and the extra power will serve the battery well with more energy harvest. On this day, for the 450-watt module, there's less than 1% loss due to power shaving. That's the energy above the red line. So almost all the excess power over the 350-watt module can be used for charging. So systems that experience a lot of intermittent sun and shading during the day are very good candidates for oversized arrays. And the trend towards bigger modules at a lower cost per watt is good for systems that can benefit from oversized arrays. So with that said, I'm going to hand off to the presentation back to Aerel so we can share some system design examples.
Excellent. Thank you very much, Mark. Appreciate that. Okay, so the very first thing that we're going to talk about is make sure that we're clear on series versus parallel. Of course, this is very straightforward, but we figured we'd cover it. So if we think back to early physics, when we connect batteries in series, we are increasing the voltage and we are keeping the current the same. When we wire things in parallel, we are increasing the current and we are keeping the voltage the same. These are very important concepts to understand when we're sizing arrays, because especially going forward, your array design may be constrained by 3 different mechanisms that we'll talk about. That could be current being too high, could be open circuit voltage being too high, or in the case of MPPT controllers, it could be that the total rated power is exceeding the rating of the solar charge controller. So as we navigate through some of these real world examples, just want to make sure that we're all on the same page when we start talking about different series and parallel configurations. On the next slide, we're going to be talking specifically about the 385 watt module shown at the top. So that's basically manufactured by JA Solar. It has a current of 10.17 amps and a voltage of 49.04 volts. What you're seeing here is a subset of half of one of our array structures. So the way that we have wired this is that every one of these structures has 2 TriStar 45s that support half the array. There are 12 modules on each one of these structures. Therefore, each solar charge controller supports 6 modules. The way that these strings are done in the current design results in a total current into the 45 amp TriStar of 30.51 amps. We're well below the current limit of 45 amps, so we're good there. Our total voltage is 97.08 volts, and so we are good there as well, well below the 125 VOC limit. The total system, just for reference, comprises 48 modules, 4 structures, 8 TriStar 45s for a total system wattage of 18.5 kilowatt. For those of you that are curious, or for what it's worth, this is not a made-up example. This is actually a system that we're working on right now for a large mining application in South America. So it's a very good real-world example to think about. What we are going to do here is we're going to look at a couple what if scenarios for this current design. What if we had 550 watt modules rather than 385 watt modules in stock? Would the system still work? So when we put in those new 550 watt modules with a current of 14 amps, compared to the current of 10.17 amps on the 385, you can see that now we're at 42 amps. We're still under our 45 amp limit, so great, everything still works. In this particular case, it would be a non-issue if we wanted to move up to 550 watt modules. If we did, the total system would be 26.4 kilowatts. So what does that mean? It means a couple things. On one hand, our total system wattage could increase by 28%. That means that we could potentially drop an entire power station structure and still be in excess of our old original rating, which seems great on the surface. Who wouldn't love to drop an entire power station structure worth of metal and charging and everything else? Or we could keep that extra power And that would result in increased life of the batteries because we have extra power to keep the batteries in an average higher state of charge, which is going to result in a longer life. Or we could let the customer run additional loads to use that extra power that we may get from the 550 watt modules. Seems like a pretty great situation. But there is, of course, a but. Those 550 watt modules are 25% physically larger than the other modules. So in our particular case, for our power station structures, and as you'll find with many other mount designs, both SunWize and others, these rails are all cut around the traditional module form factors that we've been seeing for a long period of time. So the actual physical layout of the 550 watt modules would not work on our power station. And our wind and snow loading ratings would not be applicable anymore due to changes in weight and surface area and things like that if we were to expand the rail lengths and redesign our power structure. And then, of course, the individual loading of the modules may have an implication if you're changing from 50 to 63 pounds. So just be aware, we're talking both electrically and physically. And these scenarios require careful thought of every different part of the system before we jump and assume that something is going to be a benefit or a hindrance. So let's look at the next example. Rather than using the 550 watt version of a JA solar module, which is essentially the latest and greatest version of the 385 watt that we ended up using for the design anyway, let's pick a different 550 watt solar module. Same power rating, but a different module. You can see text is a little bit small, but the current and voltage have gone from 14 amps and 49.9 volts to 18.56 amps and 38.1 volts. If you were to choose a different module, same power rating, our design would not work and it would break. In addition to still breaking physically, the design would not work electrically either. In this particular case, if this was done with foresight, you could upgrade to a TriStar 60 amp charge controller and the overall total material cost is not going to be super significant in terms of the overall system size. But as we'll see and discuss later in the presentation, this isn't really so much about the material costs in upgrading to either a larger PWM charge controller or from a PWM to an MPPT charge controller. If everything's done with foresight and care, I don't think those are going to be the primary issues and concerns people are going to run into. Where things start to become very impactful are things like racking and balance of system components, especially depending on how far down the road on design or manufacturing you may be to unwind those. Also, if you're making a significant change, that could affect drawing revisions. You may need to update bill of materials in your system. Customer documentation or installation drawings may need to be updated. It could result in customer confusion. The larger charge controller may require more enclosure space. And then, of course, this could affect companies' reputations if we make mistakes and have to unwind those because we're not thinking creatively, having foresight, and making sure that we have a knowledgeable partner to navigate some of these challenges. So what I'm going to get into now is obviously a very complex table. I want to start with a couple of important notes. First of all, what are we looking at? Okay, so what we're looking at is on the left-hand side, we have a list of common Morningstar, PWM, and MPPT charge controllers, SunSavers, ProStars, TriStars, and ProStar and TriStar and SunSaver MPPTs. On the top, we have a variety of solar modules going in size from 270 watts in roughly 30 watt increments up to about 480 watts, and then starting to go in slightly larger increments up to 670 watts, which is kind of, where the module manufacturing output is at for common latest and greatest 210 millimeter solar modules. So I have a note on the legend at the bottom. And so these color code changes mean one of three things. The first is that there is a required sizing change due to one of the three rules that we talked about: exceeding current, exceeding voltage, or exceeding rated power capacity for the charge controller itself. The other scenario for PWM charge controllers is the scenario where we have exceeded the current rating of the charge controller, but we're in between that range of 100 to 130%, where it may have marginal performance, but it may be something that would work if it's done, cautiously and with the knowledge that you may have some power clipping and output reduction for that solar module. And then the third is the power clipping for the MPPT, where we're in excess of that 130% of the rating. So we've got the electrical parameters up at the top for each one of the solar modules. You may be able to see I have a couple of these cells bolded, and we're going to go through a couple of the specific scenarios that I find most interesting to discuss. And then in addition, we can refer back to these, although I'm not going to have them up on every slide, where we essentially have the current limit when you have 2, 3, 4, 5, or 6 module strings in parallel, as well as the string voltage limit when you have 2 or 3 solar modules in series. Okay, so the first scenario that I want to talk about is this cell highlighted in blue, where we are putting 3 270 watt modules in parallel on a ProStar 30 amp. So I want to highlight this difference between sizing rules amongst manufacturers. If we follow conventional wisdom and standard sizing practices, which everybody should follow, unless you have specific confirmation from the manufacturer, which is that you should be looking at the ISC rating of the solar module. You should be multiplying it by 1.25, and you should be going up an integer value to the next highest rated solar charge controller. So if your limit is 11.5 amps, choose a 12 amp charge controller. So while I'm saying here that you could use 3 270 watt modules in parallel on a ProStar 30 amp PWM, right from the get-go, if you're talking about a different manufacturer, this actually would not work. So right off the bat, we have this variable in play here about what sizing rules apply. And of course, to keep things simple, we recommend just sticking with Morningstar, right? Makes it very easy, and they provide this extra design flexibility and buffer for us. Okay, to highlight this, I want to show a quick example of the Morningstar string sizing results as Mark McHenry was speaking to. And you'll notice here that in this particular configuration, we have an ISC rating that is actually in excess of the rated charge controller value. But because the IMP rating is below, Morningstar is saying that this is an acceptable design. And again, we're kind of on the edge here, so do take that with a grain of salt, but I want everybody to understand these nuances and the tools available with Morningstar to address this sort of stuff. So the next scenario that I want to talk about is 3 large format modules in parallel, again, on a ProStar 30 amp. So if you look at this 390 watt module right here, and as we approach this 390 watt to 415 watt range, we're essentially reaching the edge of our IMP current limitation for 3 modules in parallel. This is an important point because this design configuration is extremely common. Part of the reason for that is sort of several-fold. One, again, the 3 large format modules on a side of pole is the largest array size that we commonly see for side of pole mount applications. And because side of pole mount applications are the most common mounting mechanism, it's a natural fit for the upper limit on power consumption and array design sizes for a side of pole mount. The PWM 30 amp is also the largest PWM charge controller that fits SunWize's ecosystem of standard backplates. So that's basically the charge controller control panel that fits inside of our enclosures. Because we have sort of a universal ecosystem of compatibility, there are huge implications for us when we move beyond this 30 amp PWM to the next size up PWM TriStar 45. So we've been treading, we've been very aware of the fact that this is a common application for us. And officially, we're sort of at this point where we're constrained at this sub 400 watt module to hit this sweet spot on power density on a small PWM charge controller that will fit within all of our various enclosure situations. Now, there are sort of two obvious choices forward on this. On one hand, if you expand out to the right a little bit, if you jump up to a 530 watt module, you can achieve a similar power for the total array by putting two of those in parallel. But what you don't want to do is try buy three 440 watt modules and put them all in parallel on the solar charge controller. You got to have that foresight and that awareness to know that if you want to keep your power rating the same, don't just buy the next module size up. You may need to jump several power classes up in order to make the design translation as seamless as possible. Alternatively, you could upgrade to a ProStar 40 amp MPPT, which is what we've done in a lot of cases. This offers several advantages. First of all, you're going to get the power performance benefit. You also future-proof your loads in your designs potentially for the future, and allowing for up to 15% load growth. If you go down here to this bottom line for the ProStar 40 amp MPPT, you can see that you can achieve 1.34 kilowatts by putting two of the very largest modules in series, actually, which again is going to give you some of those small balance of system improvements as well. So some interesting opportunity for long-term cost optimization and design optimization, but needs to be done very cautiously because in between those 2 points, there are a lot of landmines, some of which we'll talk about here in a second. So we're going to talk about cold weather temperature considerations for a little bit, and I want to highlight this cell in blue down at the bottom, and I also want to talk about one other thing. So when we're thinking about the VOC limitations for this table and what I'm calculating, I am not assuming a given reference temperature. I'm not assuming 0 degrees C, I'm not assuming a low temperature for a given environment, I'm just assuming ambient conditions. So please be aware that I'm highlighting this one in particular to say that yes, you may be lulled into a temptation or not be running the temp comp calculations because temp comp calculations may not have mattered for your design up until this point. But here is a quick example to demonstrate the importance of keeping these temp comp calculations in mind as these module growths start to increase your total VOC. So the one that I'm going to talk about in question here is this 400 watt Jinko Tiger N type. It's got a module VOC of 46.05 volts. And so if you were, say, in a climate like San Diego or something very, very warm and consistent, and you truly put in a record load temperature of 10 C or 50 Fahrenheit, if you go through the math for calculating the temp comp, you would look at the delta on STC. STC is 25 C, we're at 10 C, therefore change in STC is negative 15 C. You would multiply that by the temp comp rating on the module, which in this case is negative 0.28% voltage per C. That gets you this number, which results in a VOC of 143.95, which is under 150 volts. And if we go to the next slide here, you'll see is acceptable when we put this through Morningstar string sizing tool. And again, in that particular case, it would be, but you're right on the edge and you want to be very cautious, because when you're talking about voltage and not current, you're playing with fire when you're playing on this edge. Because if you have exceptional weather events, we all remember when Texas froze not too long ago, or if you cut it too close, you could definitely be in trouble. To highlight that, I'm going to take this exact same scenario and I'm going to run it at 0C rather than 10C. And while you'll notice that the VOC itself is slightly under the 150 volts, we do recommend some buffer there, and Morningstar will start to flag you when you get within that 96% range. And again, this is just based off the testing that I've done, but you don't want to bring yourself up to the bleeding edge, even if you've accounted for an exceptionally low temperature. So just be mindful that I would recommend between 5, maybe even 10% buffer here, while assuming the worst case low temperature that you're going to experience. So just to highlight what we've been talking about here, the changes and transitions that are going on are resulting in larger module growth, which is changing both power output and physical size. And this is being driven by optimization around grid-tied commercial size solar installations primarily. Long term, I see this as a benefit as total cost of ownership for off-grid systems continues to drive down due to improvements in module manufacturing and economy of scale, cell efficiency, so on and so forth. However, in the short to medium term, there is potential for growing pains that need to be navigated as some of these battery charging design scenarios change rapidly with these module characteristics. So the takeaway is, if you do not have robust in-house solar design resources to really effectively navigate this stuff quickly and easily, then do consider the benefits of an expert partner like SunWize to help navigate through these changes. And last but not least, module electrical characteristics are no longer as predictable or linear as they used to be. You used to kind of be able to look at the increase in power rating of a module and say, well, I kind of know what that means in terms of the VOC and the ISC. That is definitely not necessarily the case anymore. And to highlight that, I'm actually going to go back a couple slides. And I want to highlight on this one, if you look at these 600 watt and the 670 watt modules, you'll notice they have very different electrical characteristics for voltage and current. And if you look at their cell stringing configuration, you start to see these new layouts that I have not seen before, which are in these novel 2x10x6 or 2x11x6, rather than the traditional 6x12, 6x24, 144 half cut, etc. So while you used to be able to extrapolate some of the implications from module growth, that I don't think is as much the case anymore. So at this point, I think we will go to any more questions. And then we'll also talk about a few more examples if we need to here at the end.
All right, sounds good. So I have the questions open here, Aerel. Let's take a look. I see, I don't know if you're able to see these questions as well, but it looks like there's a, early on, Gail asked a nice question about center of gravity in dealing with pole mounts. Do you see that question, or do you want me to read that for you? And it looks like it was answered by one of your engineers, but I think this is something that the whole audience might benefit from.
Yeah, why don't you go ahead and read that?
Okay, sure. All right, so the question is, why do you not have center of gravity in the larger side of pole setups by having the array top extend over the top of the pole? And do you see the answer, or do you want me to read the answer that one of your engineers gave?
You can go ahead and read the answer, Mark.
Okay, let me read it, then you can embellish if you would like. So the answer here is a lot of installations have poles that extend past the top of the mount. They may be mounting antennas, lights, or other devices above the array. If this is a concern, there are top of pole mounts that place the center of gravity directly above the pole. Okay, anything else you want to add to that, or should we go on to the next question?
I think that's a pretty good explanation, and we can circle back to that if there's further questions based on the answer.
Okay, very good. All right. Let's see what other questions. All right, here's a question coming in from Bill Flores. Oops. What works the best to power a water pump? A low voltage, high current system, or a high voltage and low current system? And do you see the answer there that I'll just read the answer that one of your engineers submitted, and then you can embellish if you'd like. So the answer here is generally using a higher voltage will reduce the cost of the system, since the lower current will allow you to decrease controller size, wire size, and current protection.
Yeah, I just want to emphasize the fact that the whole circuit protection balance of system side of the control panel is really driven by current. And so that's one of the things that we alluded to briefly, but it's not just the charge controller and the mount that may be affected by this. If you go up to a larger module that has a different series fuse rating or a much higher current, you need to translate that downstream, which may result in significant design changes in some applications. So in general, better to minimize current because it's overall going to keep the cost of the balance of system side low, because those costs go up with current rating.
All right, very good. I see a question from Bill. With MPPTs, is it better to max the voltage or the amps inputs? And he says with PWMs, I assume the amps should be max, as it's going to cut off the voltage anyway. And the answer we have here is that with MPPTs, you actually want to max out total power. That's voltage times current. You do need to be careful with some MPPT controllers, as the current rating of an MPPT is its output rating and not the solar input rating, which may be lower because it allows a higher voltage. So that gets into the DC conversion that happens with MPPT controllers. So thanks for that controller. Thanks for that question. Let's see.
I'm just kind of chuckling at this next question. I can go ahead and read and answer the question.
The one from Sean, go ahead. Yeah.
So Sean's got an excellent question. With the large scale commercial and residential market driving solar panel size for off-grid, do you see the lower wattage panels becoming unavailable or more cost prohibitive? And the short answer is that, yeah, basically. And just kind of as an indication of that, you know, SunWize as a company has been buying like a lot. I mean, obviously we kind of had some disruption there with the tariff ruling from the Biden, the proposed potential tariff review from the Biden administration, which got put on pause. But that kind of caused some disruption in supply on the large format side of things. And, you know, it'll be interesting to see where things recalibrate. But certainly, like not too long ago, there was a moment where we were scrounging specifically to find this power class of modules and stock and hoard them because of, if not certainty that what you're saying is going to happen, then concern or risk that it may happen, and us wanting to protect ourselves and our clients. So absolutely a consideration.
All right, very good. Thanks for that question. Let's see, a question I see here from Ben. Let's see, which CSI master format does the solar generation fall under? Do you have CSI MF documents available for specifying consultants like our firm? Is that one you're able to take, Aerel?
I'm not sure. Can we get clarification on what CSI is in this context?
Yeah, let me, actually, maybe if Ben could text us that. Let's see. Yep, no, I don't see that because I'm not sure exactly what he's referring to there. So if Ben's still on, if he wants to text us that, it looks like he's, oh, contractors, whoops, Contractor Specification Institute.
That may be one that we can take offline with you, Ben,
Yeah.
and start up an email dialogue on to get you some more direct answers. So that's something probably I will talk with our team about.
All right. Let's see. How about, can you see the other question that Ben asked underneath that, Errol?
Like when
That's something that-
retrofitting additional capacity to the existing system, is there a digital or otherwise method of syncing the 60 cycle AC sine wave outputs of multiple disparate systems? So I guess, Kyle, I would be curious to hear your take on that as well. It sounds more like an output inverter syncing thing than necessarily an array side of it, but I guess depending on what sort of coupling design you're doing, it could be more complex than what.
Yeah, generally inverters have, if you're trying to sync up their AC outputs, they need to have some sort of communication between each other so that they can sync that together. Retrofitting is usually a really difficult thing to do. You may have to replace that, just replace the old inverter with a newer one. If you can't find one large enough for what you need, you may need to replace it with a type of inverter that can be paralleled with another inverter of the same make that can communicate back and forth with each other to sync up their cycles.
And just to throw out a quick example, right? The SD series from Cotec, Kyle, does have that parallel and syncing capability. Is that correct?
That's correct. And there's outback inverters that can do that, usually through their comm hub. And Magnum's got that capability. Schneider's got that capability. Most major manufacturers have inverters that can have that capability, but you need to make sure that they have that before you do that.
All right, very good. Let's see. I did see some questions that came in about pricing. So if you have pricing questions, you can just direct them to SunWize. And I know the last slide here is a contact slide with contact information for SunWize. Actually, if you want to go ahead and bring up that last slide, you can contact either of us. But if it's pricing questions, you can just direct them towards SunWize. Let's see. I did see a really nice question here. It said, let's see, what is the average life expectancy of a solar system? What components have less life expectancy?
Oh, great question. This is a great question because it touches on a couple good design principles to keep in mind. Here's how I would break it down. I would say typically the thing that you're going to have to think about first and foremost is battery replacement interval, right? So if you're using lead acid batteries, depending on the application, I'd say, hopefully you're not getting less than 3 years, although there could be some super specific situations where you might, if you have really, really high temperatures or something like that. But typically 3 to 7 years is the range that I throw out there for battery replacement intervals. Pretty much everything else in the system beyond the batteries, I would put in the 10 to 20 year range. And really, it should be quite long. It should be more in that 15 to 20 year range. But of course, things do happen. And you may have situations where other things might fail. But ideally, solar modules, most of them come with a power performance warranty that's in that 20 to 25 year range. Certainly, most of the core power electronics, if you're using high quality equipment like Morningstar stuff, could easily run very long time. I don't know, Mark, what's the longest charge controller in the field?
Well, I mean, we still have people that, I mean, we were founded in 1993. I don't know if we can go back quite that far, but I mean, we hear 15, 20 years and more.
For sure.
Now, I don't want to tell people, I mean, our warranty is 5, and I don't want to tell people that your charge controller is going to definitely last 20 years, especially if you have it in a really rugged environment. But there are many that have been 15, 20 years or more in rugged environments.
Yeah, and if you've got a volume of system installations and it's designed properly, on the average net, I think you should be expecting something in the 10 to 20 or more year range for pretty much everything except for the batteries. Now, the thing that I want to point out is that there's two important things here for the design consideration, which is why I like this question. One, yes, those modules will still produce power after 20 years, but they're probably going to be producing about 80% the power that they were when they were new at the end of their life. And then same thing for batteries. You know, every time you go through a battery replacement interval, when you first get it, it's going to have nameplate capacity. And then over 3, 4, 5, 6, 7 years, you're eventually going to get to the point that the capacity of that battery is probably closer to 80% of its original capacity. And that's sort of like the indication point on when you're getting close to the failure drop off on capacity for a battery. So from a design standpoint, if you're being really, really conservative and you're thinking that far into the future, design the reliability of your system at 80% your new battery capacity and 80% of your new module rating. Therefore, when your system is at the end of its design life, it will perform the way it was designed at the beginning.
All right, very good. We're come to the end of the hour here, but I think we can just take a couple more questions. One question here is about when are we going to see global supply chain issues getting back to normal? And I'll give kind of our answer, and then Aerel, you can give your answer. But from our end, and I see we had another Mark from our company kind of answer this, and he really just said it depends, and he kind of says it's like whack-a-mole. We get some part situations under control, then only to find new shortages. However, shipping costs have come down and shipping times are improving, so that's definitely a positive. And he also mentioned that we do a lot of smart design with advanced software, so chip shortages affect us as well. And if I could give a number to it, I mean, I'm just going to kind of throw it out there. I'm not necessarily the best person to ask about this, but when I do ask others in our company who are more involved with this than me, they say that it's, we're going to have issues into, 2023, and we'll see how things go when we get there. I don't know how you would answer that question from your end, Aerel, but if you want to go ahead and take a stab at it, go ahead.
I think we're hoping for the best, planning for the worst. Nothing's changed.
Okay, gotcha.
In terms of our outlook, I should say, we're not trying to hold a crystal ball and make any decisions. Let me put it this way: we're not making any decisions based on the assumption things are going to get better yet.
Gotcha.
And I see another good question in here, Mark, that I can take a stab at because I was going to touch on this as well. This is a question on bifacial modules. Can you please touch on the increased output of bifacial panels? Is it overall output increase or just primarily ISC or VSC? Seeing output increases of over 20% advertised. Does Morningstar Online Calculator account for these panel behaviors if specified? Super great question. Mark, can I defer back to you on the first part about how Morningstar is treating the electrical parameters on the string sizer for bifacial modules? Are you using the electrical parameters with the bifacial output included or not? Do you know?
I believe we are, and I think I'd actually, if I had an example, we could go into the string calculator, and it might even have that particular model that they're looking at. And we could look that up.
So yeah, we can circle back on that. We could take that as a note, Trevor, and we'll get final confirmation on the string sizing portion, but I'll answer the rest of your question. So here's the deal with bifacial, and I'll kind of go to a next slide, just so I could speak about some of the rest of this. Yeah, so just like I said, that this whole table is kind of dependent on the background variable about what manufacturer you're talking about and what rules apply. Of course, this whole table gets massively shifted when you're talking about a bifacial version of these modules. Every single module I have listed here is a monofacial. So they do actually have, these 670 watt modules that are not bifacial. They also have bifacial versions of them. I believe that I have it right on my Excel file to the right of this. In this particular case, the bifacial equivalent of this exact 670 watt module has an ISC of 22.5 versus 18.5. So let's see here. And that is at the maximum 30% output, which is pretty close in line with the 20% increase that you're seeing. The thing that I want to emphasize on the bifacial modules, aside from the fact that you know, everything that we talked about needs to be accounted for the bifacial production. So it's another huge variable that gets thrown in the midst of all this. What I want to emphasize about bifacial modules from our standpoint that makes it tricky is sort of 2 or 3 things. One, when it comes to sizing the charge controller, you need to use the maximum output assumption of the bifacial modules, which in my experience is always pretty much listed as 30%. So they'll give you an electrical specifications table for the base monofacial output and then bifacial output at 5, 10, 15, 20, 30%. You got to use that max 30% so that you're being conservative in your electrical design. And that's going to carry all the way through to your balance of systems and circuit protection. So all your circuit breakers, all your wire, everything needs to be sized around the assumption of that bifacial output. It's also going to add a ton of weight to the module. It's also potentially going to be bigger than the monofacial version, but here is the most important thing that I want people to take away. All those things that I just said are going to impact your cost because you're going to have higher rated circuit protection. You're going to have a higher rated module to support, you know, the bifacial output, all that sort of stuff. But when you're sizing it from a reliability standpoint, all the people that I know are only applying about a 5% output to it. So you sort of get all the penalties in terms of design cost with the full 30% output, but you as a consumer or a user are only seeing the 5% benefit on average that bifacial is actually going to produce in a real world application for us. Maybe 5 to 10%, but I certainly don't know anybody that's banking on anything more than that when they're doing the design reliability analysis. So it's a whole other variable in all this. You got to treat the worst case scenario electrically, but from a design from a design performance standpoint, you kind of got to take the conservative approach and stick with the minimum benefit, which is in that 5 to 10% range. Great question, though.
Okay, I think we have time for one more question. There's actually a couple people have asked a related question. That relates to lithium batteries. So the question here is, are your charge controllers set up for both lead acid and lithium batteries? And the answer is yes, especially for our, all of our MPPT controllers are, and our TriStar PWM and ProStar PWM. Actually have some nice features with the ProStar PWM and ProStar MPPT where they have a lithium foldback temperature provision that can help protect against charging lithium batteries in when the temperatures start to delve into towards 0 degrees Celsius. So the answer to that question is for most of our controllers, yes. And then I guess the question for you, Aerel, along these lines is, do you recommend lithium, or when do you recommend lithium versus lead acid in your designs? That's probably the best way to.
Great question. How much time do people have? So no, simplistically put, there's a couple areas where they're very attractive. One, first and foremost, when you don't have extremely cold environments and they need to be outdoors, right? For those of you that don't know, for us, kind of one of the big question marks is charging of these lithium batteries in very cold environments. So if you're in one of those places and you're in an outdoor system application, potentially at a high elevation, that's still a challenge and a major, factor in terms of designing what we're going to do. Cold temperature issues aside, one, obviously weight. We do have applications where we had one not too long ago where, because of a whole bunch of reasons, they're actually having to cart batteries by hand from like where the truck can get to the final site location. And so they're specifically requesting a smaller battery that's lighter weight. We've had things where, you have shipping requirements or helicopters involved or planes or any number of other things where the weight of each individual battery unit is constrained. If you have conflicting design influences where you need a certain amount of power, but you also need a certain weight limitation, lithium can be a great option. The other one is if Battery replacement costs are outrageous. If you're sending PhDs via helicopters to the top of a mountain and you need to do that 5 years into the project, but it's going to be a 10-year duration, you may very well be better off putting in a battery from the get-go that doesn't have a planned maintenance replacement interval. So that's another consideration. Probably one of the most common ones that we've seen is for rapid charge and discharge cycle applications, where it's all about how much energy you can throughput on the battery, and having some of these lithium batteries that can truly support 2C continuous charging. For those of you that don't know what that means basically double the rated capacity of the battery in current input, something definitely lead acid batteries cannot do as well. Then that's another one. And then of course, we've had some unique applications where, like drone towing devices for truck loading facilities, where they're dragging around semi-truck trailers on like drones. And these drones are powered by lithium batteries, and they go through like a 45-minute load cycle where they're towing semi-trucks, and then they go to a docking station to charge. And they're just doing that over and over. For those applications, you're actually going to utilize those insane cycle lives that you see on lithium batteries, like 10,000 cycles at 50% DOD. Well, if you're doing like 14 full cycles a day, then you're actually going to need those outrageous cycle lives. So those are just a couple examples we've seen where lithium is definitely a preferred fit over lead acid.
All
just
right.
another quick one here, Mark.
Yeah, go ahead.
Just one more quick one, just because this is for you. This is a question from Lincoln on EMI output, so noise emissions from charge controllers. My understanding, right, is that we've got the jumper on the sun savers for the low emissions option, and then outside of that, typically want to stick with the PWM side of things, but I don't know, maybe Mark, you could speak to anything else beyond that.
Yeah, so I'm trying to see the exact question here. I did see that he's talking about
which controller type to select if EMI is a critical concern, PWM or MPPT.
Yeah, so as I understood it, usually that occurs with the PWM controllers because they have the quick switching. On and off switching. And you're right, there is what you can do is, so I guess to answer that question, hopefully I'm answering it the right way, is that if you can use an MPPT, I think in your system, you might not have that problem. But if you really need to use a PWM, well, and that's the one you're using in your system, there is something you can do by cutting the cable, I know, on the your PWM controller, and there's a trade-off there. You're going to get rid of the interference, you're going to get rid of the noise, but you're going to lose a little bit of charging capability. Is kind of the best short answer I could give to that question. And with that, is there anything else that's pressing? I know there are some other questions in here, but I think some of them we're going to have to take offline. Is there anything else here that you think we need to take at the moment, Aerel, or are some of these other ones the ones that we can take offline?
I think this is a fine breaking point. I'll go back one more slide here really quick to the contact information. If you have a pressing question and you have not put it into the chat, we've got a variety of forms on our website. You can definitely reach out to us. If there is a question that was put in chat that we did not get to, we will follow up with that offline and get that answer to you directly.
All right, sounds good. So thank you, Aerel. Thank you, everyone from SunWize, and big thanks to the audience for your participation with us here today. And we'll see you next time. Stay tuned for future webinars. And as Aerel said, just if you need to contact us, there's the website and phone number info. So we'll leave that up for a couple more seconds, and we'll close this out, and you will all get a recording of this broadcast emailed to you tomorrow. Thanks so much. We'll take care. This concludes the broadcast.